Charles Hand from Spokane, sorry. He's an environmental and civil engineer. He's going to be talking about managing AMD during design and construction of the expanded Bunker Hill Central Treatment Plant. Charles?
Thank you, Dave. It's quite a mouthful. So first of all, I just want to say I'm honored to be here to present at the 30th anniversary for MDOC. So thank you for having me. And you know, a reoccurring theme across a lot of the presentations and talks we've had over the past couple of days have been on water, right? Water, water, and water. Risk management around water, challenges associated with water management for new mines, existing mines, tailings, impoundment facilities, and some of the strategies employed for sites across Montana and really across the U.S. So the topic I'm going to present on today is an upgrades project that we did for the Bunker Hill Central Treatment Plant located in Kellogg, Idaho. And the plant was built in the 70s, so it's a pretty common issue in the mining industry where we have outdated or old infrastructure that needs to be upgraded or improved. And we also had to manage updated discharge limits, which I've also heard in various topics. I think this applies across several other areas, including like tailings, dewatering projects as well. So I felt like this would be a good topic. You know, I easily could have probably picked 20 different topics around this project, but I'll focus on that, kind of the management of mine water during upgrades. So to get through the project, I'll go through just some background on the mine itself, the Bunker Hill mine, spend a little bit of time on the old central treatment plant prior to the upgrades, go through the overview of the upgrades project just to provide some context around some of the challenges that we had to face and some of the constraints on site that we had to work around for the upgrades project. We'll go into methodology that we use to manage acid mine drainage during the upgrades project, including the use of temporary equipment, which we called the temporary treatment system, and wrap up with some performance and cost for consideration as it may apply to other sites. So the project site is located in Kellogg, Idaho. It's in the Panhandle, northern Idaho. And it's just about 35 minutes east from Coeur d'Alene, sandwiched in between the Spokane Valley and Lookout Pass. Just on the south side of I-90. It's a little bit of history for the mine itself. The mine was founded by Noah Kellogg in 1885. He was looking for gold, ultimately ended up finding silver instead, and began production in 1891. Throughout the operational time frame of the mine, he ended up pulling about 35 million tons of ore, over 5 million tons of base metals, which is about a little over 8% lead and 4.5% zinc, over 165 million ounces of silver. And in 1981, due to a drop in zinc prices, the mine shut down, and the area impacted by mining operations became a Superfund site in 1983. The Bunker Hill mine has what's called the Kellogg Tunnel. It's the main entryway into the mine, and it extends back into the mine 2 miles approximately. The Kellogg Tunnel receives mine water from a couple of different sources. The first being gravity components or water that flows in from upper reaches of the mine. This tends to be much higher metals concentrations, typically lower flows unless we have a spring fresh out event where we see higher flows occur, and lower pH. Mine water also gets collected in the lower reaches, or what we call the mine pool. And there are mine pool pumps that pump up from the pool into the Kellogg Tunnel, where water mixes with the gravity component. Gravity drains from the Kellogg Tunnel down to the central treatment plant, which is located, central treatment plant's located off to over here on this side. Central treatment plant was used to treat the acid mine drainage by neutralizing pH, generating sludge, and then sludge was pumped up onto this CIA, this little tiny mound, which is actually a substantial tailings impoundment area that's lined. And we deposit solids in a sludge pond that sits on top of that. This is a flow diagram of the existing CTP process. So the Kellogg Tunnel up in the upper corner would typically flow down into the aeration basin, just a lined basin built up. And that would get mixed with lime conditioned sludge that was mixed in a rapid mix tank that would flow into this aeration basin, neutralize to a pH of about 8.5 or so, and then flow through a flocculation process into a clarifier, 236-foot diameter clarifier built in the 1970s, and then flow out into a big polishing pond, and then ultimately out to Bunker Creek, which was the existing outfall. Sludge for this system was managed either by recycle back into the rapid mix tank to seed the process, or it would be wasted up on top of the central impoundment area in an existing sludge pond. There's a lined pond as well that was existing. It's a 7 million gallon lined pond that would be used for emergency storage. So if the CTP ever went down, we could automatically divert water into that lined pond, store it, and then pump it back down to the plant when the plant was brought back online. A little overview of the central treatment plant itself. The CTP is located down here, clarifier, polishing pond, aeration basin, lined pond located to the west for emergency storage, and then sludge pond for sludge disposal located up on top of the central impoundment area. A little bit better image down from boots on the ground. You can see the aeration basin tucked in here in the background, just built up on this soil bermed up area with a rapid mix tank. They had existing lime silos as well located in the foreground, and then the 236-foot diameter clarifier in the background. Big thing to take away from this is just take note of everything sandwiched here in between the lime silos and the clarifier, because this was essentially our workspace where we had to upgrade the existing central treatment plant. So pretty tight fit in there. So the CTP Upgrades Project itself, the objectives were to update the process to be able to produce what we call high density sludge. The old process produced low density sludge, which was about 10% solids by weight. We had to update it to start producing 25% solids. And that would increase the life of the existing sludge impoundment area. And then we also were contracted to build a new sludge impoundment area as well. We had to meet lower discharge limits. Part of that, a lot of that being driven by a new outfall being located in the South Fork Coeur d'Alene River. And a new groundwater capture, collection, and conveyance system was installed, and that was to capture groundwater flowing underneath that central impoundment area. So the plant in its entirety had to actually be upgraded and expanded to start treating 8,000 gallons per minute instead of what it was treating was no more than 2,000. And as low as 500 GPM when we just had gravity flow coming down from the mine. We also had to add a polishing process, which included multimedia filters to polish up to 5,000 GPM. And one of the big overarching objectives of the project was to improve reliability and redundancy of the CTP. So being able to handle variability from the mine, water quality changes, and just improve the overall process. Just briefly to look at the change in discharge limits. These are average, monthly average discharge limits, so not instantaneous maximums, but you can see across the board we saw a reduction in metals. Cadmium and zinc being two of the primary drivers and indicators of both plant performance and also the requirements for the upgraded process. And then I should note that TSS didn't really change with the new limits, but we had to target a TSS of around 1 ppm, and that's because of correlations between TSS and zinc. If we started to have higher concentrations, we could potentially have zinc exceedances. So several project challenges we had to work through. Remember that aeration basin that was built up right in the middle, sandwiched in our project work area. Well, that was going away. Essentially, we had to replace it in its place, which was our work footprint. We also had poor site soils that we had to manage. So we had to preload several areas to build new concrete reactors and new thickener. We had to manage large variability in flows and water quality, lime demands associated with seasonal variability and the way that the mine actually was operated, whether it be pumping water back or for just receiving gravity from the mine, which again, lower pH, much higher concentrations of metals. We had to find a way to work around and integrate the clarifier into the process because we didn't want to replace it. it couldn't manage sludge density much greater than 10%. And again, we had to get above 25%. So we had to find a way to integrate that into a new process to be able to meet that sludge density objective. Had very tight cost and schedule constraints, which involved actually operating the contract with the Army Corps of Engineers as a design build contract. And then throughout the entirety of the upgrades project, which is the big focus of today's talk, is the need to actually continue to manage AMD throughout the upgrades project. So, we couldn't just churn off a spigot and stop mine water from coming down to the plant. We had to find a way to actually treat it throughout the entirety of the construction project. So it was an interesting challenge. So we ended up, and there's a lot on this page that I'll actually probably jump into in the model, but we ended up adding new reactors, multimedia filters, new outfall, upgraded the sludge management system, including a new sludge thickener. And then we did implement a temporary treatment system to manage acid mine drainage during those upgrades. And as part of the upgrades, we had to install a new PLC, MCC, and integrate that into an existing system. And again, all this done under a design build operate contract with USACE, Army Corps. So this is the new flow diagram. Hopefully that shows up clearly with the dashed lines. These were all the existing components. So you can see the mine, the influent feed pipelines, the line pond, the clarifier, all those existing components that we had to integrate into the system. Well, we had to build everything new right all around it, including new reactors, big concrete reactors to treat the mine water, and also now new groundwater that came into this plant as well. Built the new rapid mix tank or reactor system where we conditioned sludge with lime, so similar processes before, but recycled quite a bit more solids back into the process to start generating that high density sludge. The clarifier was incorporated into this process, but the sludge management system changed. We would continue to use this to generate about 8 to 10% solids, but we implemented a recycle system to bring it into a new 105-foot diameter sludge thickener where we could thicken that to 25% solids or greater. And the sludge thickener at that point would then be the primary sludge management system where we would either recycle back into the process for seed or we would waste up into a new sludge impoundment area. So this is a new lined sludge impoundment area that we constructed under the contract as well. And you can also see we tacked on the pressure filters for the polishing step prior to discharge to the South Fork Coeur d'Alene River, which is a new outfall. So this is a model snapshot. This kind of shows you a lay of the land. And the big thing here is remember that image where we were kind of looking back towards the plant and I pointed out the lime silos, the big aeration basin that's kind of just sitting right in the middle of where the thickener is and part of the reactors and the existing clarifier. So a big part of the project challenge is we had to actually work within this same footprint. So we had to come in and build, big 125,000 gallon concrete reactors, 2 of them, rapid mix tank, the new thickener, new filters in the background. And the filter building is sitting right on top of that old polishing pond that I pointed out previously. It's a pretty tight workspace. So the question is, or one of the biggest challenges of the project was how do we get from this point, which was the existing system, again, clarifier, polishing pond, aeration basin, to this point, which is, again, clarifier, lime silos, and everything in between being demolished, removed, and new equipment being placed in its location while treating mine water the entire time. And our only emergency storage, again, being that line pond with its limited capacity of about 4 million gallons, which gave us less than a week of storage capacity. So we couldn't shut the plant or the process down for more than a week. Well, we had built an overcomplicated roadmap, but a couple of key points on the roadmap is for us to be able to start the demolition project itself to get rid of the old CTP, we implemented what we call a TTS or temporary treatment system. So we installed some key tie-ins, put in reactors to be able to continue to process water. And then we designed the system in a way to operate the temporary process and the existing CTP in parallel. So that's to mitigate project risk. So we could start the temporary system up, prove it, make sure that we're doing it in a controlled environment so we won't have any concerns with exceedances prior to taking the old CTP components offline, demolishing it, and then opening the way for construction of the new components. The other key point where the temporary system fit in and tie-ins included getting through construction of the treatment plant components itself, and then being able to start up the new CTP, generate high density sludge, again, with that temporary system in operation in parallel if we need it. So we could commission and implement the new CTP in a controlled environment. Once we prove that process, then we could come in and demolish the temporary treatment system and finish closing out the project with some of the upgrades that could be done kind of on the ancillary or the exterior of the main work area. And in total, this was about a 4-year project, which included a lot of the upfront design, operations, commissioning the new system, and then a 1-year O&M period and handover to the Idaho Department of Environmental Quality. So temporary treatment system, key objectives, we had to continue to manage acid mine drainage during the upgrades project. We had to consistently meet discharge limits during those upgrades, and we had to continue to be able to manage low density sludge during that process. And two key objectives were to provide a safety net for demolition of the existing CTP. So again, to help mitigate project risk while we had to go in and do these upgrades. And then also to provide a safety net when we brought the new system online, because anytime you bring a new system online, right, you're learning and you're trying to implement systems in a controlled manner, piece by piece, and then needing to work through process optimization. So it gave us a way to mitigate risk throughout that process as well. So a lot of data here. Big takeaway though is this shows the flow variability that we had to manage. We designed the temporary treatment process for a 1-year period of time. You can see we had quite a bit of variability with some pretty good peaks around the spring freshet, which we saw around June timeframe, sometimes back here in May as well. And that'd be accompanied with a big increase in lime demand, a big increase in metals concentrations as well. So much more sludge generation and sludge management requirements. And then, so this shows zinc. I'm using zinc as sort of a surrogate to not busy this too much, but you could see, again, zinc seasonally influenced spring freshet, where we'd see increases fourfold, 4 times, up to almost 400 ppm compared to an average of about 92. So key elements of the TTS design. One of the main elements was how do we get water from either the existing mine or the existing feed system of the CTP to this temporary process to be able to isolate the existing CTP and demolish it. So we ended up using the line pond, which gave us some buffer capacity. It helped equalize influent feed to the process as well. I'll jump back real quick. And then we brought out 3 mixed tanks on trailers, so mobile tanks that we were able to bring out and then essentially just simulate what the aeration basin was doing, but more efficiently, given that they're designed with updated mixers. Used new process blowers to oxidize the AMD in the reactors. To continue sludge management, we tied into the clarifier and routed sludge back to the temporary process. And then we also brought water back to the clarifier from the temporary system for discharge. And that allowed us to bypass that aeration basin. Those existing lime slakers we were able to reuse and just bring lime slurry from the slaking process over across the road to the temporary plant and just had a local dosing system. And then we ended up implementing a PLC over at the temporary system. And that was one of the key elements because it enabled or allowed us to be able to integrate the temporary system into the existing CTP in a controlled environment, and then also to be able to remove the temporary system from the overall process control system for the new plant as well. So flow diagram for the TTS, and the main things I want to point out here. So these are the 3 reactors that replace the aeration basin process, each about 18,000 gallons, with the blowers feeding into the first 2, third just for residence time. And then we had some key tie-ins for the line pond shown up here, key tie-in for the clarifier down here, and then the local lime dosing tank where we use the existing lime process with a key tie-in to feed slurry over to the other side by the temporary treatment process. And this is a layout of the TTS. So you can see on this side the 3 reactors that we used, again, to replace that aeration basin process. The lime system over on this side for local dosing. We were able to contain all the pumps and blowers here, lime feed pumps, process blowers, transfer pumps. And then the little control system, including PLC and control panel over here on the other side of this pad. And in total, it didn't take up too big of an area. It was about 80 by 70. And we just surrounded it by ecology blocks that were on site and reused material from the demolition project, such as stairs and wood and various materials throughout. So this is a pretty complicated figure, but I just wanted to point out some of the tie-ins for the civil work. So the line pond used to come in and feed the aeration basin, again sitting south of those lime silos, sandwiched between the lime silos and the clarifier, which is over here. So we had to tie into that and route it around so that way we could essentially open up that whole area for construction. We had the key tie-in for the lime slurry to bring lime slurry over because we were no longer going to send lime slurry up into that rapid mix tank. The key sludge tie-in back here, all the way back on the other side of the aeration basin to get sludge over into our process. Again, that way we could isolate this whole aeration basin and open it up for demolition. And then we had discharge that we needed to bring back into the clarifier that we routed out of the way of the construction. Used the existing MCC with just a 200 amp feeder cable that we brought over to the temporary treatment system. So this is a layout of the temporary treatment system. You can see it here in the foreground. So the reactors, lime system, the dosing pumps, transfer pumps over here. And then in the background, you can see we've opened up essentially this entire area. You can see the aeration basin is being demolished in the background here. We're starting to preload an area for the reactors. Again, because of those poor site soils, we actually had to build up a preload area prior to building concrete reactors. Big old polishing pond in the background here that had to be demolished and then filled in for the filter building as well. So you can see demolition occurring back here. And this is actually a neat figure because you can see kind of the relationship of where the mine is relative to the CTP. The line pond is kind of further out of view over here. So the performance and cost of the system. So this was that same influent zinc figure we looked at previously, just extended it after start of commissioning of the temporary system. So you can see it's still dealing with a lot of variability in zinc. We didn't quite have as bad of a spring freshet this year, so we didn't have as big of a spike, but still around 92 milligrams per liter coming in to the plant. On this side, you can see the effluent, and it's a very busy figure, but the main thing I wanted to point out is you see all the scatter associated with seasonal variability, changes in mine flows, and then this line right here where we started commissioning the temporary system, spent about 2 months or so over in here somewhere, running that in parallel with the CTP to prove that process again so we could mitigate project risk. Worked through some optimization of that system, and then once we got that system dialed in, you see we actually got these scatter points to drop quite a bit, and our average ended up dropping actually lower than our future discharge limits. So we had really good performance. I mean 0.144 versus 0.24 for the discharge limits. So a little bit on cost. The temporary equipment that we mobilized to the site, so those trailers, those pumps, Ended up costing about $423,000 for a 1-year rental period. That's how long we rented it for this project. Installation cost, this is back in 2018 timeframe, was $1.3 million, or about 65 cents per 1,000 gallons of design treatment volume. And then you can see kind of the breakout of cost over here for the temporary system. I'll highlight the civil costs for being a large portion of it, given the tie-ins, and the mechanical cost being another large portion, given the placement of equipment, tie-ins, above ground piping. The TTS cost for operations was very similar to the existing system, even including the rental costs, which is about $2 million per year. So operators, lime, electrical, and that equates to about $250 per 1,000 gallons of mine water treated. And just to put things into perspective, in terms of the overall project, so the Capex for the upgrades project was roughly $40 million. The TTS was about 1.3, so about 3% or less of the project cost for the CTP upgrades. The breakout in cost for the Capex is pretty similar. You can see in this plot here. Although we had, again, more on the civil side for the TTS, given all the tie-ins. We had a bit more on the instrumentation, INC, and electrical, given we did bring out a PLC and had all the integration associated with that. And then, of course, no concrete for the TTS. So we didn't have that concrete piece. The OPEX for the CTP ranged from $3 to $4 million for the upgraded. Big range because that plant was designed for 2,000 to 8,000 gallons per minute. The temporary system in comparison is about $2 million per year. So the CTP is about $150 to $250 per 1,000 gallons treated, depending on the flows, and the TTS is about $250. So in conclusion, we had multiple project challenges that we had to work through, including a tight schedule and cost constraints. One of the bigger project challenges was the continued management of low density sludge and acid mine drainage, and not being able to shut off the mine for more than a week. So that required strategic planning in several areas. Those tie-ins were a big part of that integration between the existing CTP, the temporary treatment system, and the new CTP. We were able to manage AMD with a temporary mobile system that we brought out within a couple of months and had it hooked up. So pretty quick process. And then during its operation, after dialing in, we were able to easily meet the existing discharge limits. And then we actually met future discharge limits for zinc specifically. Cadmium bounced around a little bit during operation. And then, at less than 3% of the project cost, it ended up being a reasonable, cost-effective solution for this project specifically. So with that, any questions? Yes, sir.
I may have missed it, but did you have to heat that system, especially early and late in the season?
Yes, the question was, did I have to heat that system depending on the season? And yes, we did. So we had heat trace that we had to install for the temporary process during the winter time.
Just heat trace, you didn't have to heat the interior?
Correct. Yep. Yep, it had about a 20-minute residence time, and we flowed consistently through that process.
Other questions?
Okay.
Thank you very much.
Yeah, thank you.